Again, how to do experiments with analog electronics is now part 3. The earlier video was part 2. I did not indicate that, but anyway, perhaps interesting to show, this was that for the second video in the final part, the final minutes, where I talked about the dissipation in a classical bipolar transistor. I didn't talk about MOSFETs, no problem, another issue, etc. This is the classical series regulator circuit, and many circuits are on my YouTube channel. Good circuit, always worked properly, though there is dissipation in the transistor, but for say 10 watt, 20 watt, 30 watt circuits, this is a good solution. Let's talk more about this first issue, how to connect, of how to do experiments with circuits that are frequency dependent. And I have already talked about that in video 2. We have here an amplifier. We send in the signal here. Say it's audio, could also be high frequency, but anyway, say it's audio. This capacitor forms a frequency dependent unit. That means that this amplifier gets a certain frequency band where it operates at its best, and of course there is now in this situation an endless resistance between these two capacitor plates. That means that in fact that resistor is in the order of 10 mega ohm, 30 mega ohm, but when that has also an effect on the back coupling, say the frequency where it works at its best. But anyway, when you lower that value, say 1 mega ohm, this is a time dependent circuit, and you can often see this, for instance, in digital circuits. Say as far as I know, I'm not very much acquainted with digital circuits. Say a 4007, correct me if I'm wrong, capacitor here, the next 4007 or 4001, perhaps I'm wrong, but anyway, back coupling capacitor, and the whole circuit oscillates in the megahertz range. Not the aim of this video to tell something about digital electronics, digital oscillators, but anyway, perhaps interesting. You can find this circuit in many forms on the World Wide Web, on websites about electronics, etc, etc. And I'm almost sure that on my channel that circuit is also somewhere in the 1200 videos that I have approximately published. Let's go to an amplifier circuit. And I take the classical grounded emitter circuit with a NPN transistor. That means that we have here the positive and here the negative. Often this is on ground, not always, but anyway, I'm talking about an amplifier circuit now. Good values, 12 volt here, here 0 or anyway, here 27k, 10k, 1k up to 3k, and here a 1k, here a input capacitor of 1 microfarad nonpolar, and here an output capacitor of 1 microfarad nonpolar. I say by purpose this is a nonpolar capacitor because it is the key to success, and I say that especially for not my followers during the past 10 or 12 years, but more for the people that are following my channel since 1 year ago or a few months ago anyway. Audio in could also be, it could go in this case to approximately 1 megahertz. The transistor BC547B or a high frequency transistor. The BF199 is a good transistor for that purpose. I don't tell the pin connections in this case because it's more or less theory here. When you send in here an audio signal, let's say 10 kilocycles sine wave, and you connect your scope here, input here minus etc etc, sine wave in etc etc, you will see that 10k see sine wave here. Surely you will see that. But what happens when you change the resistor here, the potentiometer? That depends completely, the amplification, the frequency band where that works, depends completely on the value of this capacitor. So it's 10 microfarad for audio, it's say 50 nanofarad for high frequencies, and then I mean not too high, but approximately 800 kilocycles maximum. Then you have here an amplifier, and it surely works, you can test it. But the more interesting thing is regarding the experiments, how to do experiments with analog electronics. Important. Now I tell that it is 1 microfarad nonpolar, but you can limit the frequency band by using a capacitor of a smaller value. For instance, 10 nanofarads is always a good idea, but also it could be 10 picofarad. Of course, that is an enormous order of magnitude. I know that for sure. But it can work very good. Especially 10 picofarad in a real high frequency amplifier with one transistor, and of course in such a case don't use a BC547B, it can only work up to approximately 10 megahertz. Use a BF199, that's a real VHF or high frequency transistor, and in this case you can amplify a high frequency in the order of 10 megahertz, 18 megahertz. For higher frequencies, other circuits are better usable. They are on the World Wide Web, and then I especially mean the grounded base circuits. They are often used for VHF, very high frequencies, or ultra high frequencies. But in this case, with a 10 picofarad capacitor here and a 10 picofarad capacitor here, you can amplify these high frequencies. Of course, I did not talk about what's present here at the input of the amplifier and what's present here at the output of the amplifier. When we see that bare lead here and let it hang into the air, there is, say, a resistance between that bare lead and ground in the order of 30 mega ohms or so. That has, in a certain way, at least theoretical, an effect on the frequency. In general, there is here a impedance, and an impedance is a complex resistance consisting of a resistance, capacitance, and even in many cases inductance. And at the output of that amplifier we have in fact the same impedance consisting of resistance, inductance, capacitance. Don't take this too dramatically, especially for audio. This is no problem at all. The over impedance in a broad sense, so coming from audio amplifiers, input, output. So this is very sloppy, but I only want to give the idea. The overall impedance in audio amplifiers is in the range of 500 ohms up to 10 kilo ohms. And the reason is that the noise level must be kept to a substantial low level. Noise, when the impedance here or here is very, very high, such a circuit is very vulnerable for external influences. That could be electromagnetic influences, electrostatic influences, etc., etc. And especially when, for instance, here is a field effect transistor. Such a field effect transistor can get immediately defective when it gets a too high static voltage on its base. That does not apply to a bipolar transistor that I have indicated here, but anyway, in audio, to keep the hum level and disturbances level low, the overall impedance in all these stages audio is in this range. And of course, when I say 500 ohms up to 10 kilo ohms, I'm talking about DC resistance. But it is a certain way to talk about the problem. That also means that when you make such an audio amplifier, want to keep the noise level, etc., level low, make shortcut here the output, or make in a kind of way the output in this range. Let's say 10 kilo ohms. Seems good because the second stage has also a certain impedance. Perhaps important to tell. This is the first stage with a certain impedance, and here is the second stage that also has a certain impedance. So here it enters a second transistor, and that transistor has by its natural impedance from the base to ground a certain impedance. But to keep it fixed, you can of course use a resistor here, and always important, don't shortcut your amplifier to ground. So use capacitor here, capacitor here. Now the input of the amplifier stage is not shortcut to ground because there is a capacitor here that blocks DC. Anyway, thanks for watching. I hope it was not too sloppy. It's purely beginners information. Perhaps you can use it. Thanks for watching.